Morning students. Today we start from Ampere's circuital law. It means A C L. Okay. This states that the line integral of magnetic field around any closed loop is equal to mu naught times the current I passing through any surface, the surface enclosed by this circle, enclosed by the closed loop. Okay, circle is a loop. Once again, the line integral of magnetic field around any closed loop is equal to mu naught times the current, okay, passing through any surface enclosed by the closed loop. That is, line integral B into dl is equal to mu naught I. The proof of this is, for this we take a wire of infinite length. Consider an infinitely long straight wire carrying a current I. Then the LHS of this equation is B into dl, the line integral of B into dl. This is equal to B dl cos 0. From figure you can see that for a straight wire the magnetic field is in the form of circles. Okay, so the direction of magnetic field is anti-clockwise because the current is going upward. This is by thumb rule. Okay, so at this point the direction of magnetic field is this, and we are taking an element of length dl. The direction of this element is also along the direction of magnetic field B. Both are in same direction. Okay, so cos 0. Okay, cos 0 has the value 1. Cos 0 is equal to 1. So we get B into dl. Okay, but B is constant, so it is taken out. Then we get B line integral of dl. By this we get B into 2 pi r, because the line integral of dl is equal to 2 pi r. This is the circumference of circle of radius r. Okay, now the magnetic field due to an infinitely long straight wire has a value mu naught upon 4 pi 2I upon r. So we get line integral of B into dl is equal to mu naught upon 4 pi 2I upon r into 2 pi r. Now by r is cancelled, by 2 to the 4 is cancelled, by pi is cancelled, then only mu naught and I remains. Okay, so line integral of B into dl is equal to mu naught I. This is Ampere's circuital law. Okay, this law is applicable only for closed loops. Okay, it is an alternative form of Biot-Savart law. Okay. This is the first application of Ampere's circuital law. That is, magnetic field due to a current carrying circular wire. Okay. This is the circular wire. Okay. As you know that the circular in cross-sectional and cylindrical in length. A wire is cylindrical in length and circular in cross-sectional view. Okay. So consider a portion of circular wire of infinite length. This wire has infinite length, so dotted lines are shown in figure. Okay, let A be the radius. As you can see from the diagram, A is the radius of this wire and I be the steady current, means constant current. I be the steady current flowing through the wire. This current is steady, this current is constant, and this current passes through complete wire. Okay, distributed uniformly. Okay, so three cases arises: the magnetic field outside the wire, magnetic field on the surface of wire, magnetic field in the interior of wire. Okay, so we need one loop that is known as Amperian loop. What is Amperian loop? A loop which we use for the application of Ampere's circuital law is called Amperian loop. Always remember this. Okay. Now the outer Amperian loop has radius r. Inner Amperian loop have radius r1. So first we take magnetic field outside the wire. Okay. For this, to calculate the magnetic field, draw an Amperian loop with radius r. This radius r and center O. Center is here. This circle passes through the point P. As you know that by the thumb rule, the magnetic field is in this direction. So this tangent gives the direction of magnetic field, and also at point P the direction of element dl is along magnetic field. It means both are in same direction. Now apply Ampere's circuital law. According to Ampere's circuital law, it means ACL, B into dl, line integral of B into dl is equal to mu naught I. As you know that B and dl both are in same direction, so we take cos 0, then line integral of B into dl cos 0 is equal to mu naught I. Cos 0 is 1, so we get B into dl line integral is equal to mu naught I. Now B is constant, so it is taken out, then B line integral dl is equal to mu naught I. But the line integral of dl is the complete circumference, that is 2 pi r. So b into 2 pi r is equal to mu naught I. So b is equal to mu naught I upon 2 pi r is the magnetic field outside the wire. From this we can see that magnetic field B is directly proportional to 1 upon R, or we can say that magnetic field is inversely proportional to the radius R. It means if R increases, then magnetic field decreases. So as we go away from the wire, then magnetic field decreases. Okay, the topic is same and the case is second, magnetic field on the surface of wire. Now the case of the magnetic field on the surface of wire. At surface of wire, the radius r of Amperian loop becomes the radius of wire, that is A. So magnetic field is equal to mu naught I upon 2 pi A, because we know magnetic field is equal to mu naught I upon 2 pi r. So put r is equal to A, we get B is equal to mu naught I upon 2 pi A. This is the value of magnetic field at the surface of wire. Okay. Now the case third, magnetic field inside the wire. Okay. For this we take this Amperian loop of radius r1 with center O. Okay. So in this case the current enclosed by Amperian loop, because in this case the Amperian loop does not enclose the complete current I. This current I is uniformly distributed throughout the whole wire. Okay, so current enclosed by Amperian loop IE is equal to total current upon area of circular wire pi A square, and we want only this circular portion, so pi r1 square. Okay, by this we get the current passing through unit area, and we required for the area pi r1 square. Okay, so this is the enclosed current. Generally we put R1 is equal to R because we are deriving the formula. Okay, so we put R1 is equal to R, so enclosed current IE is equal to I upon pi A square into pi R square. By this we get IE means enclosed current is equal to I R square upon A square. Now, according to Ampere's Circuital law, ACL, B into dl, line integral is equal to mu naught IE, enclosed current. Now, as we have in case first, B and dl are in same direction. Similarly, for this, B dl cos 0 is equal to mu naught, and put the value of enclosed current, that is I R square upon A square. So we get B into dl, because cos 0 is 1, is equal to mu naught I R square upon A square. Okay, so B is constant, it is taken out, then line integral of dl is equal to mu naught I R square upon A square. Now the line integral of dl is 2 pi r1, but we take r1 is equal to r. So 2 pi r. B into 2 pi r is equal to mu naught I r square upon a square. By this we get magnetic field B is equal to mu naught I r upon 2 pi a square, because one power is cancelled out. From this we can see that magnetic field is directly proportional to the radius r. It means if r is increases, then magnetic field increases inside a wire, okay, and becomes maximum at surface.